Complex ions. Complex ions are formed when species called ligands form coordinate bonds to a central species, such as a transition metal ion. So an example could be Cu2+, and in this case, you have the lone pair electrons of water being donated to Cu2+ to form dative bond. So this is a possible complex ion. And another example of complex ion is formed when Al3+ form dative bonds with 6 water molecules to form this complex ion. So be mindful that the criteria to form a complex ion depends on the charge density of the central species. If the positive charge density of the central species is sufficiently high, a complex ion would be formed. And it is not necessary that we need the central species to comprise a transition metal ion. So what are ligands? Ligands are atoms or ions which possess lone pair electrons that can be used to form coordinate or dative bonds with a central species. In the forming of dative and coordinate bonds, the ligands donate the lone pair electrons to vacant, energetically accessible, low-lying orbitals of the central species. Coordination number. Coordination number is the number of dative bonds formed between the ligands and the central metal ion. So in this example, where it's tetrahedral in shape, for the complex ion, the coordination number is 4. And in the next example, where the shape is octahedral, the coordination number is 6. And we want to add that S-block metals are less likely to form complex ion because their ions are bigger and their charge is lower, given that they can only lose 1 or 2 of their electrons in their valence S subshell. And therefore, because of this, it is unable to form coordinate bonds and more likely to form ion-dipole attraction forces with the ligands. Examples of ligands. Ligands can be neutral or anion. In the case of water, it is neutral, so it can form a dative bond. And likewise for the case of ammonia, where nitrogen has a lone pair electron. When it is actually negatively charged, they could act as ligands. In the case of Cn-, C is the one that is negatively charged and possess the foreign electron. So therefore, the carbon can form dative bond with the central metal ion. And common in all these ions that we mentioned, they are monodendate, which means they can only form one dative bond. Let us take a look at Bi-Dended Ligand. Bi-Dended Ligand means that every single molecule or ion can form 2 dative bonds. 2 of the examples that need to be known, 2 of the examples that you must know for exam is ethane diode ion. In the case of ethane diode ion, you will have 2 oxygen, which is negatively charged, and these 2 oxygen that's negatively charged are able to form 2 dative bonds to the same central metal ion. The next Bi-Dended Ligand that you need to know for exam is your ethane 1,2-diamine. In the case of ethane 1,2-diamine, both the nitrogen in the amine group are able to form dative bonds. As illustrated, both dative bonds are bonded to the common metal ion. Next example we look at is a hexadendite ligand. And hexadendite ligand, the short form is EDTA 4-, and we have to remember that this ligand has 4 negative charges. In the exam, you'll be expected to know that it has 4 negative charges and it will not be told to you. So what does EDTA stand for? It stands for ethylene. Ethylene is this group. Diamine, 2 nitrogen. Tetraacetate. Acetate is equivalent to ethanoate, which is actually these 4 groups here. EDTA 4- can form 6 dative bonds because both the nitrogen has a lone pair and therefore could form 2 dative bonds to the central metal ion. And in the case of the 4 sets of CH2, COO-, we know that the O- has a lone pair electron that can form dative. And hence, because of this, EDTA 4- can form a total of 6 dative or coordinate bonds with the central metal ion. And one example to look at is your Cu EDTA 2-. In this case, EDTA has a charge of 4-, so the charge of copper will have to be 2+. And the shape of the complex is octahedral. Finally, it is important to note that the coordination number of the complex is equal to the number of ligands multiplied by the number of coordinate bonds established by per ligand. Solubility of complex ion depends on their charge. If a complex ion is neutral, then it is insoluble in water. These are some of the examples, including aluminium hydroxide, which we know is not soluble in water and is a white precipitate. So cationic complex ions and anionic complex ions will be able to dissolve in water since they can form ion dipole attraction forces with water molecules. Finally, to sum up, central species can be deemed to be electrophile. They are neutral or positively charged, and they are Lewis acid since they accept lone pair electrons. While in the case of ligands, they are nucleophile, neutral or negatively charged, and they are Lewis base since they donate electrons. These are some examples of complex ions. In the case of this complex ion, the ligand has no charge. So Ag has a charge of +1, and given that ammonia can form one ligand bond each, the coordination number is 2 for this complex, and the shape of the complex ion is linear. In the case of this complex ion, carbon monoxide is the ligand, and copper form dative bond with the Fe. Given that the complex ion is neutral and the ligand has no charge, iron would also have no charge as well. So hence the oxidation state of iron is 0. And in terms of the shape, given that carbon monoxide can form one dative bond each to the central species iron, in this case, it means that there are actually a total of 5 bond pairs and 0 lone pair, and the shape will be trigonal bipyramidal. Next example we look at is CuCl4 2-. In this case, copper has a charge of -1, so therefore the charge of your copper is 2+, and the coordination number is 4. And we need to bear in mind, when the coordination number is 4, there are 2 possible shapes, either tetrahedral or square planar. Let's take a look at another copper complex ion where ammonia is the ligand. In this case, ammonia has a charge of 0, so the charge of copper still remains as 2+. However, in the case of copper, the shape is square planar, and in the case where Cl- is the ligand, the shape is tetrahedral. But it's important to note that in the case of beryllium and lithium, if they are able to form complex ion, their shape will definitely be tetrahedral, since they are unable to have expanded octet, as both beryllium and lithium are both period 2 elements and do not have d subshell. And final example to look at is your CrEn3, 3+. En is a Bi-Dended Ligand. Specifically, it is your ethane 1,2-diamine. In this case, we need to remember that ethane 1,2-diamine is neutral, has a charge of 0, and so therefore chromium has a charge of 3+. And in terms of the coordinate number, the coordinate number is 6 because ethane 1,2-diamine is a Bi-Dended Ligand, as every ligand is able to form 2 dative bonds. So with 3 ligands, they are able to form a total of 6 dative bonds, and hence the coordination number of 6. And in terms of shape, it is the octahedral. Hence, the formula of complex ion can be expressed as such. In this case, it is clear that your sulfate is the anion. And because sulfate has SO4 2-, it now currently will be able to form MS4, the salt, which means that M must have a charge of 2+. So hence the charge of this complex ion is 2+. And given that ammonia has 0 charge and is neutral, it means that the charge of copper is 2+. And we can conclude that the oxidation state of copper is +2. And as far as water is concerned, it is just the water of crystallization. Let us take a look at another example. For example, COCl 6NH3. In this example that was given, for every 1 mole of this complex salt, if we were to add excess silver nitrate, we will obtain 3 moles of AgCl, which means there are 3 moles of free moving Cl-. What that means is that the salt will be MCl3, which give the cationic complex of M3+ plus 3Cl-, and this 3Cl- is the one that precipitate to form AgCl in the presence of silver nitrate. Hence, because of this, we now know that the complex ion is now M3+. And given that ammonia is neutral, the charge of cobalt is also 3+. And cobalt has a coordination number of 6. Let's take a look at another complex salt that involves a complex ion. And by adding excess silver nitrate into 1 mole of this complex salt, we get 2 moles of silver chloride, and therefore we conclude there's 2 moles of Cl-. And so by the same way, we now conclude is MCl2, which means the charge of the complex ion is M2 plus. So the charge of this is 2 plus. And given that ammonia is neutral and Cl has a charge of -1, we can conclude that cobalt has a charge of 3 plus, or oxidation of +3. And like the previous example, the coordination number is still 6. The shape is octahedral. Next example. In the next example, you have to access silver nitrate, we will only get 1 mole of Cl minus. Hence, because of this, the charge of your complex ion is now M plus. So the charge of this complex ion is +1. And given that chlorine has a charge of -1, we can conclude that the oxidation state of cobalt is 3 plus. Since 3 plus 2 times -1 give you a charge of +1. And now let us take a look at these two complex ions, where their formula is exactly identical. However, their color are different. The reason is because with 4 ammonia and 2 Cl minus at the ligand, there's a possibility they can be arranged in Cs or trunks. In the case of trunks, the 2 Cl minus, which has the larger electron cloud, will be the opposite side. While in the case of Cs, the Cl minus, which have large electron cloud, will be on the same side. Hence, it's important to note that complex ion can display isomerism as well. So these are more examples of geometric isomerism. So in the case of this, you find that the 2 large electron cloud of the Cl again is actually on the same side, while the Cl in this case are on opposite side. This is a geometric isomers for the case when the shape of the complex is square planar. For optical isomerism, if we were to analyze this complex ion, where C2O42 minus is ethane diorate, so it is also termed as an oxalate, and hence acronym as such with OX. Bear in mind that ethane diorate is bi-dended. So therefore, because of this, it can form 2 dative bondage. So in this case, with the same structural formula, we will also have 2 spatial arrangement of atoms which are non-superimposable. And therefore, because of this, both these structures are optical isomers. Reactions of complex ion. There are only 3 reactions that complex ion can undertake, namely redox, deprotonation or neutralization, and ligand exchange. Let's start with redox. In the case of redox, the oxidation state of the ion involved would have changed. In this case, the oxidation state of iron is +2, and it will have increased to +3, while the oxidation state of IR has reduced from +4 to +3. The thing to note is in such redox reaction, the shape of the complex ion has not changed, as all of them remains to have a coordination number of 6 before and after the chemical reactions. So the reactions involve only transfer of an electron. In the next reaction, deprotonation or neutralization, it typically happens when a ligand like H2O loses the H plus and becomes OH minus. One has to be mindful that this reaction is not a ligand exchange, as OH minus does not replace the water. The OH minus, in fact, neutralized with the H plus of a water molecule, which acts as a ligand. Finally, in ligand exchange, what you will see is that any of the ligand, like for example, in this case, Cl, has been replaced with water. And in this case, you will find that the oxidation state of the cobalt has not changed because it remains as +3 before and after the ligand exchange. So in the next example, water is being replaced with NCS minus. And in this case, cobalt's oxidation state has also remains as +3 during the ligand exchange. In short, during ligand exchange, the oxidation state of your transition metal does not change.